this is special. This conference is kind of a special because we're organizing it via the internet and not in person. So people are supposed to have seen already the videos before and the talk. So it's not necessary to give the talk again. What we want to do in these 20 minutes is mainly discuss the results within each other and ask questions. And my friend Francesco will answer all the questions we have. I have many questions already, but I let other people ask questions before.
Thanks a lot.
Okay.
So
maybe I can ask the first question. I'm actually in cold fusion. There are two questions. One is, how do you measure the input power, and how do you measure the output power? They are the only two questions I have.
A lot of questions.
That's all. Only two
Most
questions.
important.
Output.
It is the balance, money balance in the family.
So how do you measure? How do you measure the input power, and how do you measure the output power?
Okay. So I can start my talk now.
Yeah, we don't want to listen to 40 minutes of talk. We want to answer questions.
Shortly, very short. I just give a very short.
All right. Okay.
Not just talk. Okay. So I meet. So before I speak very little about Kino Srinivasan, sorry. Because I met him the first time really in 1992 in Nagoya conference, and he gave a very strange talk because he want to use nickel and light water, and all other people used heavy water and palladium. So I was very curious about his talk. I tried to do my best to meet him, and I succeeded because one nice girl of the organizer of the conference, and this nice girl named Misa Nakamura, later we marry. So in some way, I have a chance to meet her just because Kino talk. And we joke sometimes about such beginning. Okay, my talk is the way is a proposal of a new experiment. It is based on old procedure that we developed since 1994 using very big power pulse to induce non-equilibrium condition in heavy water palladium in electrolysis, and such procedure has some advantage, but the main drawbacks is the palladium is very weak, will be powder, so short time of experiments. So from about 10 years, I developed Constantan. It's a more robust material, and I want to try again such a procedure, but or advantage higher temperature up to 900 Celsius, higher power up to 100 watt, more or less, and there is a gas environment. For practical use is more advantageous. And we develop a new kind of geometry. It's like a coiled Constantan. And at the center of the coil, there is another wire, cathode-anode geometry, and we give high voltage. So in some way, it's like, in some way, gas electrolysis or discharge, typical of Pasken or DBD regime. So I finish my introduction. We want to test this new approach. Now I am ready to answer to you the question.
So answer my two questions. How do you measure the input power and the output power?
Oh, very simple. In the beginning of the experiment, we give the main power is just DC current to make the wire up to 600 Celsius more or less, and the extra power has very big peak intensity up to 30,600 watt, but for very short time. So the mean power is less than 1 watt, really. But anyway, I measure by digital oscilloscope the current and the voltage in phase. So I know how much power I send. And moreover, I measure the amount or the C current given to the pulsar. So I make a cross check. About the output power is the same before is gas flow calorimetry. So I use it for several years. I have enough experience. I make calibration by platinum heater and another external heater by tungsten. So a lot of cross calibration. Don't worry about.
Okay. Thank you. Very good.
Okay, but
Very good point.
it's a
Very
good, very, very good question. Anyway, we can go to high frequency of the pulse if the results are good. So I can go up to over 100 watt just by pulsing. But we have to see how the system replay to the stimulation. We are a little bit optimistic because last year I showed in a CC conference, we have nice data just using mild AC stimulation, not in phase. This time the stimulation is in phase, is very, very similar to the working of Otto Benz engine. We increase the temperature by a high power of Richardson regime to emit electrons. At the maximum power, at the maximum electron emission, there is a spark to ignite the hydrogen way, but not to ignition, just to ionize, but the similarity, that one. So we are quite optimistic. I hope nothing will be broken. So other people make other
So any
questions.
other questions? Who has questions? I don't see any questions so far. Let me see.
See, you're also, I'm Rajpala from IIT Kanpur.
Okay.
You also mentioned that you're using low work function oxides.
Yes.
So these are used at what is the potential imposed on these oxides?
Yeah, the low working material is one of the key parameters because we want to have as much as possible electrons from the hot wire. So we select in some way a mixture of strontium oxide mainly with activator is potassium, some iron. So the typical mixture of low working materials used for vacuum tube, very old technology, developed from example by Langmuir, given Langmuir Nobel Prize for chemistry, and several people, Child, so a lot of people developed this kind. So we take advantage of their experience, but we optimize for cold fusion experiments. We've seen the HS energy when happen start when the temperature is close to about 700, but at the 700 degree, there is a large amount of electrons. They are boiling off at the surface of the constantan, and if we have a counter electrode, this electron can be accelerated like a vacuum diode. It's the same approach in some way, but just make proper for our purpose.
These oxides, are they colored, or the color, does it change? I'm wondering if there is some particular defect structure in the oxides that are sort of important. So I was wondering, before you start operating, is the oxide, what is the color of the oxide?
Okay, the procedure to prepare the wire is before I make the wire like a sponge at high temperature, several hours, to increase the surface. Later, I paint the mixture of nitrate of strontium, iron, potassium permanganate mixture. After I make this liquid, I give high temperature to decompose the nitrate oxide.
So that'll be
Later,
about 250 degrees centigrade.
yes, about 500, 600,
Okay.
depends, 700, depends upon that. After again oxidation, again painting several times, typically 10 times, sometimes more, but typically 10 times. So we measure the weight changing, the dimension changing, the color changing, the magnetic property changing, and the resistivity changing. So every change after, so before we make a calibration without adding low working fractional material, later we check. So even the constant is not magnetic at the beginning, so we no effect. But after proper treatments, when the dimensionality increase because oxides and resistance increase, and it begin to be magnetic. So it changed. So it's not constant 100% after the treatments. Maybe some nickel, metallic nickel, island of constant, copper, only nickel, or a lot of mixture of materials. And this is useful because reduce the probability of the sintering. The drawbacks of nanomaterial is the sintering effect. So if you have a sintering, you kill the effect. So to have different materials helps a lot. So sometimes we watch with scanning electron microscope the material after preparation when it's more chaotic as possible. It works better. But this is a simple procedure. We need more systematic work, more money, some way. Anyway, okay. If you have other
Any
question.
other question?
Yeah, Professor Chalani,
Yes.
what was your best output power to input power ratio?
In some previous experiment, the best happened when we used the cappuccino geometry. I don't know if you are have habit with the Catholic priest. They have a special note, capuchin, and this geometry has the peculiarity to have very large thermal gradients up to 400 degrees in some case, in a very short dimension, 2-3 millimeters. This was the best result. Drawbacks, the material is easy to break. So for demonstration of big numbers, it's okay. For the practical use at a long time, it's not useful. So for us, there are two aspects. Before, we want to check if the effect was real with constant. To keep working, changing some parameters before we make simple notes after cappuccino notes. So we make some further test growing, and later say, okay, this is the effect is real, but now we want to make it practical for engine. So cappuccino note, I think, is a wonderful way, but too much easy to break. So we have to find another procedure, okay.
Yeah, but what was the number, the ratio?
Sorry, about 30-40% sometimes for a long time, but it happened with thin wires. So as the wire is thinner, our results are better. The best data, but only for a few days, happened with the 100 micron wires. 200 is our typical wire. Now we are all working with the 350 micron to can increase the time of operation. So we introduce pulse because a very strong non-equilibrium condition. According to our experience, only non-equilibrium condition give anomalous effect. We almost never see anomalous effect in stationary condition. We have to move, we have to make chaos in some way, but the chaos has to be controlled, not just chaos for like Brownian movement. Some control the chaos, it is the way. So not easy, but we want to try.
One more question. Did you look for any transmutation products in the reaction?
Sometimes before, at the beginning, but several years before, we watch for transmutation, and we found, especially with palladium wires with high voltage, or electrolysis with some coating, especially of glass coating, liquid glass coating, and other. We found even red earth materials. So, but it was just to see if something really strange happened. So the electrolysis with palladium coated by thorium oxide was one of the best results. Liquid thorium nitrate, I painting palladium, but it was about 20 years before.
No, I'm talking about your anomalous heat experiment, the AHE effect. I mean,
yes.
Was any of those samples showing any transmutation products?
I now don't have money to watch for this kind. So I hope to have some money from European Union. They give some money, but so I will start again. But for these specific experiments with several material added, strontium, iron, potassium, and manganese, I think it would be not so easy to discriminate about transmutation. If we found red earth materials, it's okay. But for other like zinc or other contaminant, so anyway, I want to see from time to time if this is something strange happened. It's in my program.
And how long is the time of operation when you say long?
Okay, the latest wire, 300 micron wires, worked from 1 year. But just because COVID problematics, I can enter not so long at the laboratory, 2 months con battery shut. So I have to put at low power. So I think it's no big problem. Constantan is really strong material. I estimate capability for the stress about 4 or 5 times larger than palladium, but I think now it's more. The Constantan is really very strong material. Example, up to 600 degrees, you don't get oxidation, nothing. 600. Oxidation starts at about 700. So every sort in inert gas, argon, we make test, or helium, we can work up to 1,100. We make some test. Nothing, not destroyed. It's really strong.
So for 1 year of uninterrupted operation,
Sorry?
without interruption, you are able to operate this for 1 year with
yes,
about 30.
But we make in the mild condition because several times it cannot go, so I keep the wire working but low power. Anyway, I think it will be no real problem. Anyway, the coil is so simple to build. Even 2 months working, it's okay. I just change. Like refill of of ball paint. So when the wire is thick, really no problem. And then thinner easy because the surface oxidized, so the true thickness is less. So there can be some weak point, hot spot, something like that. When it's thicker, these effects are strongly reduced. So, but we give extremely large amount of electromigration up to 3 volts centimeter. Usually, when the electromigration is over 0.5 volts centimeter, it's considered a big number. Now it's up to 6 times larger. So we expect something good.
Okay.
And we want our goal to make a engine. So no gasoline anymore, but our dream, a bit beginning for home heater, something like that. But long time perspective engine.
Yeah, this is Pankaj. Just had one quick question. You apply electric pulses,
Yes.
just very short interval, time interval pulses. Is that,
Okay.
is that something similar? First, let me, is it something similar to the, we heard Mike McCubre, and this is also shown earlier by somebody. He was talking about the super wave function, which also
Okay.
is something similar to that, or is it?
Okay.
Different?
To be true, we were the first in the world to apply pulse, 1994. Other people later copy us, just to be clear.
I see.
Anyway, the super wave is an interesting approach, but I worry why after this one experiment with very big gain, 25, they never were able to reproduce themselves. So I worry why they were not able anymore. They have a gain of 25, giant number. So if I membership of some country, I will give a lot of money to such people. But they are not able to produce because maybe they didn't understood what happened or because they depend too much on the metallurgy of the palladium. The metallurgy is very nice field, but extremely complicated. So our approach of pulsing is to make us less dependent on palladium or wires technology because the amount of external stimulation is so big. Sorry, I have to stop. Sorry, moment. Sorry, so big that overcome the metallurgical problematics or surface problematics, so on. I repeat, we give power density external of the order of 8 kilowatt for gram of constantan. Very, very big number. Okay.
Yeah. Actually, one more question. So the pulses that you apply, so
Yes.
they are probably of very short duration.
Yes,
Right.
I can. We now in the previous experiment with palladium, we use pulsing between 500 nanosecond up to 2 microsecond. We make some tests up to 5 microsecond, but we observed that the best results is up to 2 microsecond, and another aspect, the rest time and the fall time of the pulse has to be as short as possible. Means high frequency effects can be important.
So this,
So we make some tests with the coil. The coil is inductive, so we cannot go to time shorter. Example, 2 microseconds with the constant we are used. Anyway, we will see what happens. Now I make the pulsar then can work up to 10 microsecond pulse duration, but we tested up to 40 microseconds. It can, it's strong enough to work up to 40 microseconds, but just for basic study. I show data typically at 10 microsecond duration, but we have to see, maybe it's too much long because are not necessary 8 kilowatt for gram, maybe 1 kilowatt is enough. So, but we have to see what happened. So this was just a proposal. It was presented at the European Commission as our project. So it's the first time I show a possible idea based on previous experience, but new idea, completely new.
So what would be the type of electron densities that you would be able to, density distributions that you would be able to, you think that you will be able to create by this kind of pulsing?
Okay, the current density of the surface, we think is what shown in the Richardson formula. I send a picture there about Richardson formula. Supposing a working function is about 2 electron volts. There are indications, but all indications that our working with function is lower than 2, like 1.8. So the current density is really, really large. At example, as we work at 800 degree during pulse condition, we can have several 10 of ampere or more, really big number.
Thank you.
May I ask one last question?
Yeah, sure, everything you want.
Yeah. So is when you say it operates for 1 year,
Yes.
is the, let's say, output power gradually decreases or suddenly it fails?
Yes. The problem is when we observe, we have, because accident, filtering of the surface, the chest power drops always. So it's a weak point in necessary to avoid sintering.
So that'll be a gradual process.
The sintering is big. Another problem can be degradation of low working function material because change the properties of surface. So, but it's a systematic study. Usually when we see that the HS power go to 0, we dismantle and make a new one. But before, because we work, example, over 3 years without budget. So we have to optimize what to do, especially the money to spend. So we have to optimize time, money with no budget. It's not easy. Now I hope will be better with the money from the European Union, but I think it's not enough. Anyway, even better than before. Okay. So when and moreover, even in static condition, when there is no sintering, over time, in the same day, the output power decrease because we think when we change, for example, the power from current from 1 ampere to 2 ampere, we have non-equilibrium condition, new rearrangement of the system, and this means non-equilibrium. It gives HS power. Later, the system is in equilibrium again, and HS power fall. I presented such data at the MIT meeting about 3 years before. So always it is reducing, sometimes to 0, sometimes 1/3, 1/4 of the beginning. So we need continuous stimulation. Depends also, maybe stimulation every second, every hour, we don't know. So, but we think even 10 Hz can be more than enough to have big numbers. So now the systematic test in a dummy coil at room temperature is at 100 Hz test. So we give 30 kilowatt at 100 Hz for short time, obviously, 10 microseconds. Anyway, all is shown in the presentation. So if you want to write me privately or in public, I have no secret. I just want the system will work for a long time for the advantage of everybody, of the mankind. So collaboration are welcome. Suggestion, critics, everything is okay for me.
Any question? Okay. Now, I am the chief here, so I can ask a question.
Oh,
Did
sure.
I have observed that with
Yes.
copper nickel alloys, hydrogen is absorbed above, if you need to go to 700 centigrade in order to absorb hydrogen
No,
in nickel
no, no,
copper alloy.
no.
Did you observe any absorption of hydrogen in your case?
No.
Do you
no.
see a decrease of
I
pressure?
have strong proof, very reproducible, that absorption starts at about 150 Celsius. If the surface is a sponge, otherwise you have to wait maybe some months to have effect. So you have to make sponge surface, otherwise so low absorption that you can not able to detect.
Okay.
But you said immediately the resistance decrease. So the procedure to have, so the most important is the first absorption. The procedure of the first absorption is like how you born. If you are wrong for the first absorption, you keep this wrong procedure forever. So the fixed procedure is really critical. So just to say in short, the fixed absorption has to be softly and without direct current, only indirect heating. Maybe
So
you have
just
to spend 1 day for the fixed absorption, and after you can give the direct current and make everything. Okay.
same question say to both of you. So when you say, Professor Varian, when you say, how do you detect hydrogen absorption? Do you do temperature program reaction
No. Very simple. The resistance for the wire drops from itself.
Okay. So and how do
We
you,
published
Professor?
several papers at the beginning of this study in 2011, 12, 13. So there are a lot of paper. Jean-Paul published most of this, so just go to ICMNS. So really later say, okay, now is routine work, so we don't publish anymore.
I know, but to
details.
answer the question, I understand you measure the absorption by the resistivity measurement.
Sure.
I've done experiment with powders, and I realized I measured the absorption by measuring the pressure. So that's how I do it. So I know it's really absorbed. But I agree, you can do that also with resistivity. I've done this type of experiment.
But our material is for 200 micron is about 0.5 gram total bulk and surface, with the thick wire 1.5 gram. So, but irrespective to the reactor, really to check, to observe reduction pressure is not so easy.
Pressure.
Okay.
No, I agree. Okay,
Anyway,
so maybe
important, we make the reverse experiments. After loading, we make vacuum and heat again the wire, and the resistance go to the origin. That is valid only if we make this test in the 2-3 days. Later, impossible to desorb the hydrogen. Maybe something change, we don't know. But if we do quickly, 1 day, 2 days, is reversible. So there is strong proof, and it's published.
Okay, Francesco, we have to stop here because we are already late. So thank you very much.
Always I speak too much. Sorry.
Too much. I know you're Italian, that's all.
Yeah, what to do?
Okay, thank you, Francesco.
Thanks.
So now we have to go to the second part of our session. Yes. someone is speaking? No. Okay, the second
Yes,
part of the
buongiorno,
session.
Sono Anthony Zuppero. Hi, buongiorno.
Hi, hello.
Oh,
Hi, how are
Anthony
you?
Zuppero,
Yeah, how are
italiano,
you?
italiano.
Sì,
Pero,
parlavo italiano, ora non
You
parlo.
are Italian, Antonio.
Sì, sì, parlavo, no, parlavo.
Oh.
60 anni. Okay, we're late.
so, okay, so we have to talk now about the session in honor of Dr. Srinivasan, and people can share their memories, and we can also discuss the research done by Dr. Srinivasan and the future of LENR. I think everybody is interested by the future of LENR, by the way. So, I have memories, you know, I don't know when I met him. I'm sorry, I don't know when I met him the first time. It seems I always met him, you know, been like forever. We always talked about this very interesting work he was doing in Bombay, and then his work also with transmutation. He was very much interested by biological transmutation and by all kinds of transmutations. And the good thing with every time we're going to a conference, because he was a vegetarian and I am a vegetarian, he was just following me and taking the same plate, the same meals that I was taking, you know, so that was the way we're doing. He was a very, very nice person. I really miss him, and I can't believe he's gone, actually, you know. Any any memories? Who want to share?
Maybe Professor Bhaviran, maybe one thing we can try to do is we can finish this one more talk and then can come back to this, I feel.
We can do
That way
that.
the technical session can be completed and then we
Okay,
can have a more free-rolling discussion.
Is Frank Gordon here? Is Frank Gordon supposed to talk?
Yeah, I suppose that Frank,
Is he here?
Yes, we're here, John Paul.
Oh, okay. Are you ready to go?
Yeah, give me a second here.
Okay, all right. So now we have the talk by Frank Gordon about his very interesting work he has done, how to make electricity directly.
Okay, let me see. I need to figure out how to share the screen here.
Somewhere in the bottom you have a share the screen, something like that. I have in French, I don't know, screen share or something.
Okay, yeah, there we are. Now we can start the video. First,
Okay,
let me
we see.
introduce
Hey.
Harper Whitehouse, my co-worker and colleague. Going back to what you were just talking about, Dr. Srinivasan, for the first 20 years since 1989, I was the head of a department that had people like Stan Spock and Pam Boss, Ed Harper, for example, in my department, and they kept me away from the cold fusion as much as they could. You know, that was kind of a pet project. So I went down a lot to observe. When I retired, I decided I wanted to get into this and get some hands-on work. You know, I was kind of suffering withdrawal because I wasn't able to have any of the fun. And that's when I contacted Harper, and he said he didn't think it was real. And I said, well, that's good, because I don't want to waste my time if it's not real. So we talked for a while, and the thing that convinced Harper was seeing the infrared videos that Stan and Pam had taken. And actually, I was there when that work was done, and we showed that at ICCF 10 in Cambridge. And so anyhow, since that time, we've been working together. One of the first things I did was go back and look through all of the early work. And the thing that I was impressed with was how much of the early work that was done by Dr. Srinivasan and Bark is really pivotal. And in the first 4 or 5 years, in my estimation, they did some of the best work. And so, you know, I credit Dr. Srinivasan. And as it turns out, a few months ago, we rediscovered one of his papers that he and Ralph Srinivasan and others from Bark had written on the production of ionizing radiation from a cathode. So, you know, here was something 25 years ago. I think it was published in 96. There were 3 or 4 papers that were published prior to that that were kind of segments of that, but that particular paper kind of summarized the work. So in any event, I'm happy to be here at this conference and are part of it. And let's see if I can share my screen. Okay, can you see that?
Yeah, you can see it.
Okay, very good. I might have to turn. I'm presuming everyone has gone through the video, and if that's the case, you may have some questions, but as it turns out, I got questions for you too. I think I told Jean Paul at one point, it seemed like every time we learned one thing, we learned that there are 3 more things that we didn't know. Yeah, and so the problem with that is I was learning, there were more things that I didn't know than I did know. So I was getting dumber faster than I was getting smart. So to solve that problem, I simply changed the definition of smart people to include those who know what they don't know. And by that metric, I was doing real well. Let me see, I've got, I thought I was in a presentation here that did not have timing on it. So, but in any event, I can run through some of the slides, but we also have some additional slides that we've put in and discussion about the results that we have. Let me go to slide 58. One is the implications of our results. And yeah, the experiments, I think, expose the existence of low energy reactions. In fact, if you look at my presentation or the presentation we put together, LENR shows up on every view graph, but it shows up in the bottom, LENR workshop in memory of Dr. Srinivasan. We're not sure what the reactions are. And I thought last night about when there was discussion between Mike and Ed and others on theory, and Mike had talked about the need for high loading and flux. We're not sure about the need for high loading. We agree with flux, but our reactions, you know, if you take an electrode out and you just let it sit there, you really don't achieve the high loading that you would get if you have an electrochemical experiment and you can use fugacity to increase the loading. So we're not sure about the loading. And by the way, if you have any questions, you can direct them to John Paul, because he's one of the people that replicated our results, and for which I'm very grateful. So in any event, implications include, you know, that there are low energy reactions. They may be related to the biological transmutations. I used to enjoy the presentations that Dr. Srinivasan would give at the ICCFs, where he talked about anomalous transmutations of, in some cases, tons of material that should have produced huge amounts of heat, and they happened without that. So maybe the reactions that we have exposed here, if we can't produce a power supply out of them, maybe they will at least bring some funding to study the identification of the ionization and study also these low energy reactions. And I guess the question, you know, one of the questions I would have is, does nature have another low energy reaction path that so far we don't know? Harper and I have talked about what could be ionizing the gas. Something is ionizing the gas. And, you know, a vacuum tube has a way to produce ions. High energy electrical, you know, has a way to produce ions. Nuclear reactions have a way to produce ions. we're not sure that any of those are involved in what we're seeing. And so that's something that I think would be interesting to study. As far as a potential source of energy, it needs to scale up 7 to 9 orders of magnitude. In fact, let me comment at this point, the level of energy that we are measuring here is in the nanowatt range. And, yesterday, Ed Storms mentioned that he had a calorimeter he thought was good to 5 microwatts. I believe that was the number. But we're, several orders of magnitude more sensitive than that in detecting the presence of these kinds of events. If we need to scale it up a lot if we're going to turn it into an energy source. And in our estimation, increased flux is probably the primary thing. You can achieve that by increased temperature, as we've shown in some of the data, increase the size, the active area, and also improve materials. And I think all of those things will ultimately come into play. The other thing I want to point out is, at best, this approach will only improve the energy output over other heat systems by a factor of about 4 to 1. If our current high temperature ways to produce heat with your power plants are about 25% efficient. So if we're 100% efficient, we're 4 times that, unless, and this is the serendipity, unless LENR can supply some of the heat to the lattice. So one of the things that we've talked about is, do we have a combination of LENR, which supplies some heat to the lattice, and also some other reaction going on. Now, the LENR would also produce some particles like alphas and neutrons. In fact, some of the work that we did at SPAWAR on where we measured with CR39, we clearly saw that we were creating pits, and when you did the calculations, they were either alphas of several MeV, and every now and then we would see it shatter one of the carbon atoms, and we would see that in the CR39, which is indicative of a high energy neutron. But again, going back to some of the early work that Dr. Srinivasan and the people at BART did, where he said that I believe the neutron flux was, 6 to 7 orders of magnitude below what you would expect for the heat that was produced. So if that might suggest that there is a low level or a level of LENR that is involved, but there may be another reaction in addition to that is producing some of the heat. The other advantage the LEC has over some of the other heat systems to produce electrical energy is a LEC can use low grade heat. Our cells have operated at room temperature. They do better when you heat them up, but you don't need it to produce high temperature superheated steam or anything like that in order for a LEC to operate. So those are some of the comments that we have. Now, we've also done a lot of calculations, and we didn't put those in the presentation. We can talk some about those. Let me see if I can. Harper, where would you want to start here? I guess maybe we can just the supplemental material. A lot of the work involved the study of the work that J.J. Thompson and Rutherford did, and I have to say, when you study that and think that this was 125 years ago in the late 1800s, and you think about the level of sophistication of instrumentation, they really didn't know what ions were at that point, except that they determined that you had to have ions in order to conduct through gas. So this was prior, I believe, to the discovery of
The electron.
discovery of the electron, the discovery of alpha particles. So the fact that they were able to do this work in the late 1800s is impressive, and well, I guess that's why he got a Nobel Prize. And
And the interesting thing is, in trying to analyze how one of these LECs work, I still am frustrated by these observations that occurred to Thomson 100 years ago. And that is that when you set down the differential equations, which are in the supplement here, which is Frank is now scrolling through, taken from his work, the observation was that he finally came to the conclusion after he formulated the differential equation, he could not solve it. To this day, there are no analytic solutions for the electric field inside a LEC that will allow us to do a detailed analysis of what's going on. However, in recent times, now with the advent of digital computers, and I have a bibliography here of some of the work, but basically within the last 20 years, people now have written code which will allow you to solve for the electric field distribution inside parallel plate geometry, cylindrical geometry, which corresponds to our LEC configuration that we've shown in the presentation, and even spherical electrode geometry. So at least now they can do that. And when they finished all of these calculations and looked at them, they turned out to be very qualitatively similar to what me calculated by successive approximations 100 years ago when he came up with a solution, even though he could not achieve an analytic solution. And we feel that this allows us to make reasonable assessments. One of the observations with regard to heat that I would like to make is that if indeed we have calculated the rate of ionization of the gas correctly, and to do that, that is a somewhat tricky observation. You might bring up that's the analysis, suggested analysis procedure. No, you had that slide there.
okay.
If assuming that that calculation does yield a reasonable estimate for the ionization rate, then the key thing to remember is that it takes on average approximately 35 electron volts to produce an ion electron pair in hydrogen. Well, and if we indeed have ionization rates measured in 10 to the 10th to 10 to the 13th ion pairs produced per second, then in fact we are producing a reasonable amount of energy within the gas itself. And in fact, in one of my calculations, I showed on the slides that's part of the talk that this ratio is sometimes 16 to 17 times more energy is being deposited into the gas than is actually being transmitted to the external load resistance. So in fact, these cells have two outputs. They have a thermal output and they have an electrical output.
You want to say anything about this?
Frank, I have a question.
Okay.
You did the experiments with both the hydrogen gas as well as deuterium, right?
That's correct. We've done them, and it both works. We have not done enough experiments that I think I can.
Which one works better?
Better than the other at this point.
Which one works? Which gas works better?
I don't know.
So both are good.
Yeah, both have worked. In fact, these cells, just when you think you begin to understanding what they do or how they work,
the hydrogen gas you use must be having some deuterium impurities, right?
He asked if the hydrogen gas has some deuterium. Yes, we manufacture we manufacture our own hydrogen gas. It's made by reacting water with lithium. And so the ratio of deuterium would be that which is the normal ratio of deuterium that you find in water.
So on this regard, I had a question. So why do you adopt this way of making hydrogen? Electrolysis, won't that be easier?
What was the question?
Yeah, I'm sorry, wait, didn't understand the question.
No, see, I understand that if you react an alkali metal with water, you will get hydrogen and alkali metal oxide. But this is more sort of tedious way to make hydrogen, right? You can't be just electrolysis of water. Won't that be easier?
Yes, yeah, the answer to your question is yes. We're self-funding our work and buying a small rechargeable lithium battery and stripping it apart, which YouTube on the web tells you how to do, is what we did. There's a little bit of serendipity there because, you know, and we showed this in the presentation, obviously there will be a little bit of water vapor. And so we froze the cell out to make sure that we eliminated the water vapor. Turns out Cravens and Letts, I think, have done some similar experiments, and I believe their comment was a little bit of water vapor may help. So whether or not that helped or hurt, we don't know. We would like to get a tank of hydrogen and just hydrogen or deuterium and just use that. But for now, this is the way we've done it.
And of course, to make our deuterium gas, we simply use a couple of milliliters of heavy water, again, reacted with the lithium. And that way we don't have to obtain a supply of deuterium gas.
Okay, thanks.
Okay, one more question.
Yes, may I do?
Hello.
Okay, yeah, Francesco. So usually, if I well understood, the relationship between the current and the voltage is described from Child-Langmuir formula. So the current depends over voltage to 1.5. So I would like to know if you observed the same relationship or something completely different. In usual vacuum tube, the relationship between current and the voltage depends on the voltage to 1.5.
The formula that we're using is shown on the suggested analysis procedure. Following the analysis that Thompson presents in the 3rd edition of his book, the equation that he derives is that the voltage is proportional to the square of the current density with a coefficient A, followed by a linear term in current density B, and so what I have suggested in the analysis procedure is to use that formula, which is a quadratic formula, and observe that B involves only quantities that are available for us. The mobility of the gas, the charge of the electron, the separation distance between the electrodes, and a quantity which is a little harder to get, the recombination rate of the ions, and that he gives in the book. And so it's very close to that which people use for air. A good number to use for rough calculation would be 1.5 times 10 to the minus 6 is a reasonable ion recombination rate. With that, that's what I use then for doing the calculation.
But in some simple experiment, maybe about 3 years before, we found, at least in our condition, at close distance, that the dependence the current is about 1.4, not 1.5, but close to the child-Langmuir formula. Obviously, at low pressure, a few millibar. And with hydrogen or deuterium, with hydrogen maybe is better. I don't know why, but not too much different. The best data was when we had the argon in the system. At the beginning of the experiment, before we absorb hydrogen from the Constantan. But anyway, seems not too much different from child-Langmuir formula, at least in our condition, it were parallel wires, very close to each other, about 2 millimeter distance, more or less. Each wire is put inside a glassy sheet, and we test up to, if I remember, 1000 volts, DC volts, positive and negative, but were different, positive and negative behavior, but we don't find a explanation. We just found was different. And then we change, we reverse polarity after we realize. But anyway, when it works, it's not too much different from a child. Maybe still have data I can send you if you like. The fitting seems about 1.4. But with thin parallel wires, 200 micron wires. Okay, stop.
Frank?
Yes.
You mentioned this that the ions were having energy of 35 electron volt, right?
No, I mean we give power to the wire to make it hot enough, and after with the counter electrode we change the voltage from 100 volts up to 1000 step by step. And we found more or less the dependence similar to child-Langmuir law, more or less, okay, not perfect, but not too far. So at low pressure, obviously, if you just increase the pressure, or because when we, before loaded wire with hydrogen, at high temperature, there is a deloading of hydrogen, so the pressure is a little bit higher. So there are, and moreover, the voltage increase the probability of deloading. So is at least in our case is like a reaction chain. If we have a large voltage, we increase the deloading, but the load increase the pressure, so the current decrease. So complicated way. Anyway, the trend, quality trend is like that. So because this all the experiments, we decided to can have spark production with high voltage. Okay, I stop.
Frank?
Yes.
So I was asking about the 35 electron volt ions. You were mentioning that the ions that were produced were of 35 eV energy, right? Or the maximum energy was 35 eV.
Average energy required to produce an electron ion pair, 35.
Okay, so that was not measured.
No, that's taken directly from the literature.
So could the ionizing radiation have been gamma rays?
No, it's been the energies have been calculated in the literature for electromagnetic and for particulate ionization, and they don't differ significantly by more than an eV or two, depending upon what the ionizing source of the radiation is.
Did you check for gamma rays?
Yes. according to the data that I was able to find on the web. This I take from doing web research. So
Right.
the quality of it is, as is always the case, subject to going back to the source material.
Right.
No, what I meant was, did you check whether the ionizing radiation is gamma rays? So did you check it with a GM counter or a gamma ray spectrometer?
Andy did.
Sorry, I didn't understand.
Hello?
Question is there how do the gamma rays produce the ionizing radiation? Is that the question?
No.
Gamma.
He said, did you measure? Can you hear me? Frank?
Yeah, I'm not sure that we understand what the question. Yeah, what the question. Maybe we gotta ask John Paul. You know, he replicated this, so let's let's get.
What the question exactly?
No, I was asking, I suppose I'm audible, right? Am I audible?
Yes.
You're audible, Rajiv. Yeah, you're
Yeah,
audible.
so I was wondering whether you have checked whether the ionizing radiation that is being produced in your experiment is gamma rays.
Oh,
We
I
don't
don't
know
think
what
so.
it is.
Can you hear me? Andy Erickson at Los Alamos did that. Got no gammas.
Okay. So could they have been neutrons?
Don't
No, I
know.
mean, the question is that your two electrodes are not identical. The one of the electrode is covered with palladium in it. You know, there's palladium on the surface. If you don't put the palladium, it will not work. So there are gamma rays coming, cosmic gamma rays all the time, but you don't see it unless you have the right deposit on the surface. When Frank asked me to repeat the experiment, I was a little bit reluctant at first because I know that there's nothing like a simple experiment in science. You know, when you start working with something, it takes you years after that. Anyway, I tried taking a palladium silver electrodes, 2 millimeter in diameter, 10 centimeter long. I put it inside a stainless steel tube, put hydrogen in it, and nothing happened. Then I did what he did. I deposited palladium on top of it using palladium bromide as a material. And then when I did the experiment, I immediately saw a voltage. Then recently, I decided that probably if you increase the surface area, it will be much better. So I did that. That's my experiment, my first experiment, very simple. Then I tried making a larger, more surface. So I used 2 cylinders of about 5 centimeter diameter, about 2 millimeter gap. And the surface area is more than 10 square centimeters. And then to my great surprise, the voltage was huge, 740 millivolts. And if you do the calculations here with the resistivity and the voltage, you are in the microwatts, not in the nanowatts. So I think we are producing microwatts. I should have given the numbers, but it's a lot more than we had at first because there's a lot more surface. So I think when I pumped out the hydrogen, the voltage dropped to 0. When I reintroduced hydrogen, it took several days to build up again. So I think loading is important, or maybe some material change at the surface, something like that is happening. The first time it goes very fast. Second time is much slower. So there's something to learn there.
It is looking quite complicated.
It's always more complicated than you think of at first.
And
What is the difference between work function between the two electrodes?
Oh, I don't know, but it's not large. I don't think it's large. I didn't measure it. I don't know. One of my electrodes is stainless steel, and the other one is palladium. It's silver, on top of which I've deposited palladium, thin film of palladium. My electrochemistry.
Did you look for transmutation products on the electrodes after the experiment?
No, because transmutation is hard to detect, and there are so many impurities in my system. It's not clean enough so that I can do this kind of work at this point. Maybe in the future.
What about you, Frank? Did you look for transportation products?
No, no, we don't have the instrumentation to do that for transmutation. And
Let me make a comment.
Yeah.
And we have in one experiment performed several years ago, we took a cell in which the active gas was deuterium. All right. And after having run the cell for several months, we took a sample of the gas to a mass spec at the local university, and they ran a rather crude residual gas analysis of it. And it would appear that we had more hydrogen in the gas than would be anticipated on the basis of our original filling of it with deuterium. That is the only experiment that we have done where we've done anything that would even vaguely be an analysis of the residual product.
yeah, I want to go back. This slide and the next one were in the presentation. We typically sample at a rate of 512 samples per second. And here you see these spikes and so on. So this is the activity from the cell. And when COVID hit, and I don't come to our lab is in Harper's House. I don't come every day. We reduced the sample rate to 128 samples per second so that, I didn't have to come and download the computer, because at 512, you generate over 8 megabytes of data every minute. And so that adds up in a hurry. But
so these spikes are current or voltage? These are current spikes. Huh?
I'm sorry, the spikes.
These are probably
Current or voltage?
These are current spikes.
Yeah, these are current
spike. Okay.
So may I just interrupt just to answer Professor Biberian's question? So I was just checked on Google. The work function difference for iron is about, let's say, 4.5. Palladium, it's about 5.2. So that is...
It's not much, actually. It's almost the same. Yeah. Okay.
4.5 and 5.2, right? That's not significant. That is not significant, or?
It's not significant, I think. I don't see how anything can happen. If you put something else than hydrogen, it doesn't work.
No.
I mean,
what I'm saying is, what is the voltage difference you are measuring?
Oh, the best I had was 640 millivolts.
Yeah, so here we are having a voltage difference. The difference in work function is about 0.7 volts.
Mm-hmm. I see. Okay.
Because we see this in most of our electrochemical experiments, the difference between an anode and cathode work function. Supposing I use a silver chloride electrode, and on the other side, if I have a platinum electrode, just an open circuit condition without doing anything, if I put a voltmeter, I would have a difference between work function, which is quite significant. So if the difference between stainless steel work function and silver is about 0.7, is what we are measuring a difference in. What is the work function? I mean, what is the voltage you are measuring?
640 millivolts. 640.
Yeah, so the iron work function is 4.5. Palladium is 5.2. I mean, that's what I get from Google. So it's about 0.7.
Yeah, that's correct.
So you think the difference in work function will have something to do with this?
I don't know, but what I know is that you are not in a liquid, we are in gas phase, so you cannot apply the same rules, I think.
No, we are applying, no, we are putting a voltmeter to two metals. Yeah. So the work function, what is measured is the difference between work function, right?
No, they don't touch to each other. I mean, the two metals are separate. They don't touch.
But when you put a voltmeter, even under open circuit condition, what is measured is the difference between work function. See, the Fermi level difference. See, there is a...
I think what Professor Viberian mentioned was that the voltage builds up over a period of time.
Yeah, because when your chemical compound changes, the work function will change. See, hydrogen is a amphoteric material. When you put hydrogen onto palladium, hydrogen will act as an electron donor. So the work function of palladium will become even more negative. The work function difference will increase.
Yeah, let me jump in, and in the category of just when you think you know something, it throws you a curve. We thought work function was very important, as you're suggesting, and I think it might be. But this cell that I've got a picture of here has been operating at least 9 months, and it started out as, like is shown here. It actually started out at a couple hundred millivolts, and then over time it decayed. And like I said, this was during COVID, so I only was coming to the lab 1 or 2 days a week, and by one of the days I was here, it was down to about, I don't know, 5 or 10 millivolts. It was pretty low. So we thought about, well, let's pull a vacuum and give it some new gas and see what happens. But it was late in the day, so I left and went home. Okay, then the cell went negative. It didn't go to 0. It went down and actually went negative, and went negative by a pretty significant amount, almost as negative as it had been positive. And we watched it for the next couple of weeks, and then it cycled back the other way. So, if that's associated with work function, then the work function is changing in the cell during the experiments. And for example, this has the outer electrode is brass in this one. In this one, it's galvanized, which is zinc, and we were doing that, looking to see if we could determine a work function difference. And I don't know, the problem is the work function seems to change in the cell while it's operating.
And on the web, there's information that says that the work function depends upon the surface state of the material as well as the bulk properties of the material. And since we have ionizing radiation impinging upon it in the configuration we have here, the ionizing radiation can be changing the surface properties of the counter electrode. But for questions with regard to work function, I might suggest that you want to consult 2 experiments that were conducted quite some time ago. In around 1924, Kramer examined a cell composed of various materials selected for their different work functions, and published some results showed that he got different voltages when he changed the work function. Then Omat in the 50s did essentially the same experiments, and again found that he got different voltages for his cell depending upon the work functions of the materials. But in both cases, what made these experiments different is that they had to induce radioactivity. That is, they had to have a radioactive material to ionize the gas. The thing that makes the LEC so unusual from our perspective is that we're ionizing the gas with materials that are not normally radioactive. And therefore, we don't understand the mechanism yet. From the amount of current that we can draw, measured in number of electrons per second, we're drawing 10 to the 12th, 10 to the 13th or more electrons per second out of something that there's no foreseeable radioactivity. And so it's an open question, going back to what Srinivasan did 25 years ago. What was fogging his film? He didn't know the answer. We don't know what is causing the conduction.
Yeah, here's the experiment that we did. We actually used a glass mason jar, so it was about 4 inches in diameter or 10 centimeters. and we had fins, alternating fins of zinc and copper. So we were trying to see if, and get these out where if I was producing a particle here of particular energy, the Bragg curve, the bulk of the ions would be produced out in this range. And we hooked up a dBm between the zinc and the copper fin. We also hooked up a dBm between the palladium electrode, the working electrode, and the copper fin. And here you can see, and we increased the temperature a little bit, and you can see the volts between the zinc, or copper to zinc, through a 10 megohm load. And here the volts between the copper to palladium through a 5 megohm load. And these were sampled at 2 samples per second. We have some dBMs that have an optical couple to an RS-232. We switched to that because we wanted to isolate the possibility, any sneak circuits coming from our LabJack instrumentation that might be corrupting our data. So anyhow, these were the results from that experiment.
Okay, one question, Frank. In your current spike experiment, it was the driven, right? What was the driving voltage?
The spikes that I showed from the
yeah, they were current. You mentioned that they were current spikes, right?
Yes, yes. What we have here is the LabJack will measure a voltage, and so we had a resistor, and we selected the values of the resistor so that the
so the driving voltage was fixed at 5 volt or what?
I'm sorry, say?
No, the driving voltage, was it 5 volts? Because the LabJack will normally supply 5 volts, I think, right?
LabJack will measure, well, I'm not sure. Yeah. We had LabJack has something called a tick, which will put an extremely high impedance. And so, to minimize the amount of current going through it.
Why don't you go to the one where it shows the instrumentation
Yeah.
for the LabJack? Just a second.
This one here?
This one, I think.
Okay, what number is that? 11.
Here's the instrumentation we use with LabJack. We have 2 measurement techniques. The one that Frank just described earlier is a DVM, which has an optical connection. And we use that when we're trying to measure very low voltages. With the LabJack, we can measure voltages up to 10 volts using, and so what we have is we have a high voltage supply connected to the counter electrode through a current limiting resistor. And we measured then, put a 1 meg shunt across it and measure the voltage. And then we go and we put in series with it a load resistor, and we measure the voltage across the load resistor to measure the current. So we have the cell in between 2 resistors as shown here. We make 2 independent measurements. So we now have the voltage as the difference between the counter electrode and the working electrode, and we have the current measured from the working electrode to ground. And that's what we used when we make the conduction tests, which are shown in there,
Yeah.
where we, again, the other gentleman commented that he used voltages from 100 to 1,000 volts. Yes, we often put in as much as 1,000 volts and then step it down in about 50 volt steps. And we take it down to about 100 or 50 volts. And we measure then the current and voltage as a function of the conduction. And that's how we get our IV curves characterizing the conduction through the gas.
Now, in this slide, you look at, you might say, well, wait a minute, you're only putting in less than less than 300 volts. This is the voltage actually through the cell rather than the voltage that the high voltage power supply puts in. Recall we have those resistors in there, current limiting resistors for safety purposes and other sources or other paths for the current. So this is, we calculate the current actually going through the cell. So we may be putting in 800 volts from the HP power supply, and we step that down in steps of 50 volts, and that causes the actual voltage in the cell to go from maybe 290 down to 40 or 50, and you see the current coming down at the same time. So if you notice, you say, well, wait a minute, the voltage you're talking about doesn't match what's on this slide. That's because of the instrumentation and what we have put in for safety purposes, because and it's a good thing we have. I have felt a tickle a couple of times when I've touched the and not been as careful as I needed to, and perhaps not as cautious as I would have been had there not been the current limiting resistor.
Okay, so this measurement was done when the current was sort of steady, right? Not when the spikes were there, but I think after some time it stabilizes, right?
Yeah.
Right.
Yeah. This was on this particular test. We were using the LabJack instrumentation system. I think that was the test that we did here. This at this point, and this is an example, and every cell is different. These are file averages, so each of these data points is about a minute. We also save all of the raw data. Fortunately, you can buy terabyte USB drives now, and we calculate in real time the 1 second average. So we have that data that we can go back and look at. But here it went for several days. The total time span here is about over 2 weeks. Went for several days. We had a spike here, and then it jumped up and it stayed here at about this level. At this point, we did the load test that you saw on the previous slide, and then for some reason it dropped down, went back up, dropped down, went back up, and stayed up for a couple of days. And maybe we're a little slow, but I realized that based on the voltage we were putting in and the current limiting resistor, we were operating, the cell was conducting at the limit that the current limiting resistor would allow. So it was actually on a weekend. I called Harper, and he changed the electronics. He changed the resistance of the resistors, and so that we could conduct twice as much current. And as soon as it took a little bit to make that change, and when he did, of course, the voltage dropped down. When he turned it back up, the cell went up, and it was producing a little over 1,200 microamps, which was almost exactly what the new current limiting resistance would allow. So when I came back into the lab on a Monday, we decided, well, if a little bit's good, more might be better. So we did that again. We cut the resistance in half again, and you have to look at the raw data because it went up for a few milliseconds and then dropped and never recovered. So we don't know if we burned something out in the cell. If we did, that would indicate that maybe we were getting all of this conductance from one hotspot, from one or two hotspots that we then burned out. We simply don't know. But here's what the data looked like, and then the B is the load test that I just described.
Yeah, okay. So thanks, Frank. I think the cell looks very temperamental. And I think we may have to move on to the next part of this session. Okay,
well, thank you very much for your attention.
Thank you. Thank you very much.
Thank you.
Now there is a brief presentation by Kanjar Jain. Is that okay to do that now?
Yeah, okay. Is that fine? Can I just start then?
Yeah, I think
Okay,
so.
so let me just share my screen. And so here is my presentation. I just want to, I have given this talk today morning. Just want to show you, just introduce to you what we have done quickly. I mean, I won't take too much time. So basically, we want to look at a theoretical model for a low energy nuclear reactions. It may not be the process that is actually happening in data, we don't know. Just want to look at a clean theoretical model which we can study and see if there's any way that the tunneling barrier can be evaded in a rigorous sense. That was the basic motivation for us. So let me just go directly to the main heart of the question of the issue. So the process that we actually looked at was this one. Hydrogen plus deuteron goes to helium-3 and with the emission of 2 gammas. So normally this reaction is studied with the emission of 1 gamma. We want to study 2 gammas because we want to have a situation. So here it's shown pictorially. You have a D plus H in the initial state. So then you have a photon emission, and this acts like a perturbation. The, the, the interesting thing about this perturbation is that puts the system into a state which is not an eigenstate of the unperturbed Hamiltonian. So then this state is actually a superposition of all eigenstates, and these eigenstates go up to infinite energy. So the energy eigenvalues out here have to go up to all values. And then you have a second perturbation again, where again a photon is emitted, and then this goes back to, then it goes to the bound state helium-3. So this was our basic idea. And the idea was that since it's now getting contributions from all eigenstates, so they of all energies, so therefore the Coulomb barrier, which is active out here, will be reduced. And although this is now a higher order process, I mean, you have to emit 2 photons, this is suppressed, but not as suppressed. I mean, because of the lower tunneling barrier, this may not be so much suppressed. There are actually 2 diagrams, but that's a detail which you don't have to go look at. So one can compute this in this well-defined manner by this standard graduate level, something that we teach to graduate students, second order time dependent perturbation theory. And this is the full formula for this, where you go from an initial state through a perturbation to an intermediate state, and then from an intermediate state to the final state through the perturbation again, and you have to sum over all these intermediate states, n. That is a crucial point. So just to continue now, so I don't need to show this. So yeah, just to quickly mention that since we sum over all states of all energies, therefore the energies of these states can be very large. So this matrix element now can have a very much reduced Coulomb barrier. So the key elements out here are 3 key elements. One is the the matrix element which takes you from the initial state to the intermediate state through a perturbation. Then the intermediate state to the final state. This is the nuclear matrix element. Final state is a helium-3. Then there's integration over all the intermediate states of all energies. So this second matrix element, once you specify the potential, you can compute. That we have done quite well actually. This first one and the third one are the tricky elements. So the problem is that we want to invoke a state of relatively high energy, and we have an initial state of relatively low energy. Now, unless this Hamiltonian has something which varies very fast, this overlap is going to be small. That is one problem that you face in implementing this. So this actually gets solved by our proposal that you emit a high energy photon out here. If you emit a high energy photon, then this perturbation is a very short time scale perturbation and introduces a very high momentum components. So then this overlap becomes strong, somewhat large. And so this actually has a very elegant solution in that sense. The third one I'll just talk about in just a little while. So let me just go ahead. Let me show you this formula in more detail. So this is the transition amplitude. It's a bit complicated. but here is this initial to intermediate state and intermediate state to final state. So the key element over here is actually, I've done this again later on. So wait, just a minute. Yeah, so, okay, actually, maybe I should just, so the key issue out here is that I have this high wave number photon, and here is this high wave number intermediate state and a low and a slowly varying initial state. This overlap becomes significant only because you are emitting a high wave number photon in the middle. So this one has a very nice solution. I can make this matrix element relatively large. So here I actually show you this. If I did not do this, then this matrix element would be very, very small. So this I've already shown you. In fact, just to show you what the intermediate state looks like, for a KV energy, it actually is very rapidly oscillating function as a function of R. And now I show you the molecular matrix element. You go from initial state to an intermediate state through this photon emission, because the large wave number over a small range where the wave number of this state matches the wave number out here, you get a significant overlap. You see this overlap is very, very small out here, very, very small out here. In this narrow range of energies of these intermediate states, you get almost unity overlap. So this matrix element actually gets, the problem that this matrix element would have been small otherwise actually gets very nicely solved by just emitting a high energy photon. And you just need to, have some high energy process. It could be maybe a high energy phonon or something of that kind, something like that you have to do. Now the nuclear part is fine. Then the key issue is that you sum over intermediate state energies. To start off, we use intermediate state energy, wave functions to be just the free wave functions. They're basically this type with a phase shift. Those you can compute. We actually showed you one of those wave functions. In fact, this is what this looks like. This is what this wave function looks like. You can compute this numerically. Now, okay, when we did this integral now over all these intermediate states, the calculation actually failed. What happens is that you actually have this the nuclear matrix element is very slowly varying. When you take this overlap of the two, you integrate over all energies, you don't get anything out here. Then where this molecular matrix element is large, you start getting a contribution. But then this all just, because this nuclear matrix element is a very slowly varying function, this whole thing just cancels out, and there's a beautiful cancellation. The whole thing just cancels and goes to zero. The calculation fails with free state wave functions. So if you use the free space wave functions, this actually fails, and actually is consistent with what's seen probably in experiments, because the process does not take place in free space. It requires a medium, and it probably also requires a special circumstances. Now, experimentalists might tell me, some conditions under which things work, but I can theoretically now give you some ideas as to where it might work, and where it will fail. So one possible solution is, this is actually a nuclear solution, not a medium solution. Okay, so you have this very rapidly oscillating matrix element. You need something of equally rapidly oscillating. And so a nuclear solution is that you have a resonant, you look at a state which has a resonant tunneling. So if there's a resonant tunneling with a width of about 100 electron volts like this, and then it dies out, that'll give you a large contribution. That's one possibility. Other possibility is that I don't want to go through these details right now. You may have looked at it, and I can come to this later on. Other possibility is that you just, when you arrange your medium in such a way that these wave functions, actually, let me go to the punchline out here. Basically, you require some sort of a modification of the wave function of this DH system, which modification is required at large distances. It may be, you may require some sort of a special symmetry for the wave function, or you may require that the wave function is localized, something of that kind. I'll give you an example. So, the point that I'm trying to make is that I have got a system out here in which the wave function modification that is required in order to make this thing work is at large distances, that is order atomic length distances and not nuclear distances. Nuclear distances are not under our control, but atomic scale distances is something that we can actually may be able to manipulate. So therefore the mechanism has a chance to work. And let me give you an example of a wave function that'll work. Okay, here's an example of a wave function that'll work. Instead of the cosine Kr, which is a spherically symmetric wave function, you take a wave function of this type, which is just cosine kz, something of that kind. Okay, so this is now written in cylindrical coordinates, is a cosine kz wave function, and you just say that at large rho it just goes to 0. At small rho just means, you know, half of a Bohr radius, something of that kind. You know, it is behaves like this, and at large rho it just dies out, and then, you know, in the short distances, nuclear distances, this will actually nicely go over to the standard spherically symmetric wave function that we use. So that's not an issue. We can extend it. So that is really all that I want to say. So with this one, actually, it works out. I mean, this is a kind of wave function which will make it work. So I don't want to go through this. So what I'm saying is that given that I can use a wave function which is modified at large distances, not at small distances, I can create a situation mathematically which will make low energy nuclear reactions work out. Therefore, I feel that these nuclear reactions at low energies are possible. But what actually happens in experimental data, we still have to actually, go into that. This is just an illustration. I mean, a very systematic, basic quantum mechanical calculation to illustrate that this can work. Thank you very much.
Oh, thank you. So we can talk about this paper, and we can talk about everything we want now. It's a free time now.
So I have a couple of comments on the paper.
Okay.
So one suggestion might be that the WKB approximation could be helpful for your excited state calculations to work with potentials that are not flat. My other comment is that your idea of having intermediate states with high momentum to get around the Coulomb barrier or to make it through the Coulomb barrier, that concept has been discussed earlier in the literature by two Hungarians, Peter Kalman and Thomas Castelli. They talked about the idea in connection with particle interactions instead of photon interactions, but the idea, the goal to use intermediate states to deal with the Coulomb barrier was discussed by those physicists.
Yeah, I've seen that paper. I'm familiar with that paper. So,
Okay.
I mean, I don't see we are inconsistent with that. And I have given you the conditions. See, the idea works only under special conditions. Otherwise, it will not work. And there were two very, crucial things. One was the overlap of the initial state with a high energy intermediate state. In fact, first we fooled ourselves and thought that this will be all right. It is not all right unless you have a potential which actually has high wave numbers. So that actually is created by the fact that you emit a photon of high energy. So that actually, the photon of something, you have to do something of high, something of high wave number. That is what it is. You have to do something for high wave number, and that is necessary to have this overlap significant. And then you still find a problem that the energy integral still cancels out. And that energy integral, I have shown there are conditions, where you have to have some sort of a sharp variation, okay, a resonant tunneling, or I gave you an example where you actually don't have a sharp variation, but you actually need, instead of sharp variation, what you need is you need to break the spherical symmetry. Okay,
Right.
Yeah.
For whatever it's worth, I think your analysis is vastly superior to what Kalman and Castelli did for their
Well, I'm
version.
honored to hear that. Thank you so much.
Sure.
I'm honored to hear that. So any other questions? I mean, I'm waiting for questions, I guess.
Pankaj,
Yeah.
Professor Hagelstein has been talking about phonons being involved in these reactions, right?
Yes.
So how do you reconcile your analysis with his?
Well, at the moment, I don't know. I mean, one thing that I've been saying repeatedly is that so far I've talked about only real photons. One immediate generalization is that I have a virtual photon. Virtual photon just means that you emit a photon which gets immediately absorbed by the lattice site, and that actually will also excite the lattice oscillations of phonon modes. So in other words, I can actually perhaps even overlap with Peter's idea. You just have to, instead of the perturbation being induced by a photon, it may be induced by a phonon. Now I have to learn more about it. I do not know enough about it to comment on this right now. Can you have a phonon modes of sufficiently high energy? I do need something of high wave number. Otherwise this will fail. So if you can have a phonon mode of high wave number, it doesn't have to be initial, it doesn't have to be a phonon that is actually incident. It could be a phonon that is emitted from this particular state. So I mean, if that can be done, then yes, I mean, we can actually maybe even have a phonon state excitations which could induce this reaction. Something I would certainly like to look at.
So phonon energies are limited to maximum of on the general order of 100 millivolts. So the energies are certainly not there. Phonons can certainly have some momentum. However, I mean, strictly speaking, your interparticle momentum that's already in your model is a degree of freedom associated with the phonon. So you're already including that. In the a difference between your approach and the approach that we're following concerns the interaction. Photon exchange, is well understood and is what you presented. Phonon exchange is, in the condensed matter literature, comes about as, second order coupling as a result of electric or magnetic field interactions. But I've been pursuing a different kind of coupling for phonon exchange. In the simplest way to think about it, if you've got a nucleus, if it moves, then we know that there's a relativistic effect that's Lorentz boost. So if it moves fast, then there's a contraction, there's a realignment of the spin and isospin as well as a response, relativistic response to the wave function Lorentz transforming. Now, if the nucleus moves back and forth in response to phonon vibrations, when it gets moving one way, it Lorentz transforms to look like it's moving this way. When it goes the other way, it Lorentz transforms to make it look like it goes that way, which sort of implies that relativity implies there's going to be a superposition of nuclear states involved in construction, which implies there's going to be a weird kind of phonon nuclear coupling. And that's the interaction which I'm interested in. So the interaction's fundamentally different between phonon coupling and this kind of interaction.
Okay, something to think about. We can maybe talk about this offline.
Sure.
So any comments, questions, discussions? We can talk about anything we want. The future of LENR, maybe.
There was a comment yesterday that we were supposed to figure out how to get LENR to be able to be published in the mainstream literature.
Yeah.
So I have a few thoughts about that. So the first thing we recognize that this is a gigantic problem. It's a very serious problem. As it turns out, there are people who have papers published on cold fusion in the mainstream literature. Xingzhong Li succeeded in getting a cold fusion experimental paper published in JPhysB, which is no slouch of a journal. The NASA folks recently got an experimental paper into Physical Review. And there are a number of other examples. Andre Lipson got a non-trivial paper published in JETP. When Ed Storms was an associate editor for Naturwissenschaften, some cold fusion papers were allowed there. So it is possible to get some papers into mainstream journal publications. Pam Boss has an approach that, in previous years, a paper would get written. Frank's here, so he can probably explain better about how all this works. But you send it in. If it gets rejected, or if you get bad reviewers' comments, you respond to them as many times as possible. And if it doesn't work, you pick another journal. If that doesn't work, you pick another journal. You keep on going until you get success. Some other thoughts on this, that in principle, the way things are set up is that the journals, in essence, aren't interested in a paper, at least from some of the comments I've gotten both from editors and from reviewers, basically until you've solved the problem. So what that means is that if you show experimental results that are unambiguous and reproduced by others, so it's correct, and you at the same time provide a model for it, which is correct also, which is the answer, then and it can be verified by the reviewers, then you're allowed to publish. So if you think about it, it's a really interesting situation. In any other field of study, preliminary results or partial results or incremental results can be published as a matter of course. In our field, the journals basically come back and they say, well, none of this is real. If you want to prove that it's real, not only do you have to prove it experimentally, but you have to have the theory understood and worked out as well. So they're not interested in any incremental results like in any other area of science. So in essence, the way the situation's sort of been set up all these years is they're basically putting us in a position of, with whatever personal resources that we can put together, we get to solve the problem before being allowed publication in mainstream journals. Now, recently, Larry Forsley has been working with a number of accepted groups or a number of mainstream groups that have a better ability to publish. So for example, if I send in a paper, I get the full 9 yards from the editors because they know I've been in the cold fusion business forever. But Larry Forsley figured out that he works with mainstream groups that haven't been in cold fusion forever. When they send in a paper, it's treated differently. So if you have not worked in cold fusion, your chance of getting a paper published in mainstream journals is vastly higher than if you've actually been in the field. Anyway, those are some of the thoughts I've had.
I also noticed one thing from your own institute. Google published this paper in 2019, revisiting cold fusion. I suppose all of you might have read that. And Professor Yetming Chang from your MIT Material Sciences, part of that paper. And I think there are lots of experiments that are being done in MIT Material Science. And the way he seems to be, he's studying hydrogen and palladium. and he has published a JAP paper, chemistry of materials paper. He's a very well-known solid-state electrochemist, very well-known. I mean, so they talk about hydrogen palladium, but they don't mention anything about cold fusion. I mean, it looks, we read that Journal of Applied Physics paper. From the experiments, I would have thought that I suppose he's very well informed. I would have thought that he would have looked at transmutations, but they don't talk about anything about transmutation. It's like they want to look at the problem without mentioning anything about cold fusion. That is one approach I think at least he's taking. I don't know whether Professor Hagelstein has discussed with Professor Yetming Chang from Material Science MIT.
So my postdoc Florian interacts with the professor. I will point out that the Nature publication, in a sense, there was talk about cold fusion, that an effort was tried to replicate the SRI experiment, McCubery's experiment, and a very large number of attempts were made, but they didn't succeed in getting the experiments to achieve high enough loading to match the conditions required for the experiment. So in a sense, much effort was put in, but they were unable to successfully carry out the experiment. They reported, as I recall, several hundred tries to replicate the nickel hydrogen experiment. What's his name? The Russian
Parkhomov.
Parkhomov, yeah. And several hundred tries, every single one of them a failure. And so that of course reflects badly on the cold fusion field, the CMNS field being in nature. On the other hand, in a sense, within our community, there's been, on the general order of 100 efforts to replicate that experiment, and except for perhaps one or two exceptions, the results are uniformly negative. So in a sense, the Nature paper is largely in agreement with the experience in our field. Then there was a discussion carrying out experiments to try to replicate Tom Claytor's tritium production. Now, an issue with respect to that work is that Tom Claytor got positive results, and he wrote papers to explain what he did to get those results. And the experiments reported by the Google team were completely different experiments. They were not, they had very little to do with Tom Claytor's experiments, other than tritium was assayed for. So in a sense, the route for a successful paper in Nature is to, it's a little bit like the key to success is politically correct thinking. They had a negative result or set of negative results. And so as a result, with negative results, there's no difficulty publishing in mainstream journals. So Nature, I think, was very pleased to have such a publication.
I mean, the result was not entirely negative. The result that they presented was not totally negative, because they did show at 1 kV energies, they showed, a 10 times larger cross sections. And then what they concluded was that this is actually the cross section is going to increase as you go to even lower energies.
Well, so, except that if you view the field condensed matter nuclear science as having a lot to do with like excess heat production anomalies and tritium production and so forth, their paper reported negative results across the board on every single thing that they did along those lines. With respect to increase of cross-section at low energy for low energy DD collisions, that's both expected theoretically and observed in many other experiments experimentally, and is not an area of controversy and involves no anomalies of any sort. So I I do not agree that there was any support. I mean, from my perspective, now, Mike McCoubry thinks it was a glorious thing to have a paper published on the topic in Nature, but I'm not, you know, that optimistic about it. I thought that it basically got published in part because the Google team put in an awful lot of resources and got groups not in the field, would you know, to look at the problem. But you know, a weakness of it is that they were, you know, in a sense, it's not obvious that they did a whole lot of their homework to dig down. I mean, for example, if you're going to report a negative result on Claytor's experiment, why not do Claytor's experiment? You know, if you're going to do a replication of the SRI experiment, you know, why not involve the SRI team to advise more closely and more carefully and work with them to figure out how to do the experiment? Just things like that. It's just.
No, no, I'm not particular about publishing in Nature per se. How do you get it mainstream? See, one of the approach, I'm a physical chemist, okay? So anything to do with interfaces, whether it's catalysis, electrochemistry, it's very hard to reproduce in general. So one approach that material chemistry, material physical chemistry community is adopting is set of experts come together and publish best practices. For example, if I'm allowed to share my screen, I can show you something. Maybe our community can attempt to do something like that. I'll just share just for a minute if you can indulge me. So are you able to see my screen?
Sure.
Yes.
Yes.
Yeah. So there are about 20 such papers, best practices for, this is about electrocatalytic performance of nanomaterials. I mean, I can show every thing, best practice for lithium ion battery, active material with, I mean, I can show for every capacitor. I mean, I'm an electrochemist, I work in all these areas. So what I am proposing, suggesting is, see, many of you here have put in maybe 30 years of work in all these things. At least few more, specialized papers, like for example, today morning I was asking Dr. McCoubray, and Dr. Ed Stroms was also here, what, as an experimentalist, would you expect, what is the minimal model of LENR? Can we agree, can the experimentalists agree? Maybe there's not one mechanism, there are 4 mechanisms, let's say. As an experimentalist, Dr. McCoubray, few people who've been working in this area, can they say these are the best? Is there a consensus within the community? What is the way to measure things? And what would the minimal model has to explain?
Okay, so first off, it's been 31 years and 10 months, but who's counting? The second issue has to do with a different perspective on your question. So, for example, if you were dealing in an area of accepted applied physics or physical chemistry, then there isn't a question as to whether what you're trying to measure exists or not, because a lot of previous work that people agree on have been done. So the question of how best to measure it and what the best practices are is a good issue. If you're doing research in the area of anomalies, where the existence of the anomalies is not accepted, then a paper in the mainstream journal on best practices to measure anomalies that are not accepted, it isn't going to make it very far, probably.
Can I just pause it? Just one, can I add something? Just there. See, I'm not even saying that we should publish a best practice measuring paper in the mainstream journal. In JCMNS, if this is the flagship journal of the community, can we have a best practice measuring paper? This is the way of measuring. Is there a consensus?
So the short answer from my perspective is no, there's no consensus.
But maybe that's one thing where we should work towards the consensus.
Well,
Because unless maybe.
Again, I mean, your comments and your thoughts are excellent comments and mirror analogous comments that have been discussed and dealt with in our community for decades. So one issue is that the problem is very multidisciplinary. So you have people from different disciplines involved, and they focus on experiments that are close to their area of interest and their experience. So as a result, because there's relatively few groups in our field and their expertise is in slightly different areas one way or another, the overlap's imperfect. However, between SRI, NRL, NEF Frascati, and the energetics folks, they made a massive effort to try to have these four groups come together on a series of experiments, use common analytical techniques and experimental techniques to see whether they could get the same results in common set of experiments to approach the kind of thing that you were suggesting. And even with such well-supported and gifted set of experimentalists, the agreement was reasonable and it was important, but it wasn't uniform. So those folks gave a number of papers at conferences, and you can find some of their published papers and proceedings papers which discuss the need for systematic assessment of common experiments with common methods and the routes that they've presented. For example, they describe ways to measure loading using resistance ratio, where a lot of work has been put in and good results are obtained that way. There's a lot of discussion of calorimetry. So in the early days, very fancy calorimeters were employed because there were so many fundamental questions about calorimetry. But in later years, simpler calorimeters were easier to use. The experiments were faster and they seemed to work plenty well. In terms of the geometries, initially the cathodes were basically, they were big and they took a long time to load. The group moved towards cathodes but were much thinner and much quicker, loaded much more quickly, so the experiments could be done much more quickly. So in spite of all of this, in spite of all the documentation, an independent group, the Coalescence folks, went ahead and tried to follow up on what these guys did. And after a very large number of experiments and a huge amount of work, they came away empty-handed without a single measurement of an excess heat effect from any such experiments. So the answer is, at least in that particular example, is that a major effort was tried to do exactly the kind of thing you're thinking about. And there was some success, but the success wasn't quite as uniform. The one other place where they've tried to do that is the Japanese effort focusing on the nanoparticles. And in that case, there were 4 university labs combined with car companies. And the university labs, they did tests with common samples using common experimental gear and common diagnostics, and they got very similar results from different measurements of common samples. So that particular set of experiments and that bit of research is the closest that anyone's come in our field for having a common set of practices that multiple labs can execute on and get comparable results. I can't underscore the importance of the Japanese nanoparticle work.
May I speak?
Yes, you can speak.
Okay. Okay, maybe just a few comments. First one, most of us forgot the experiment made from Fralich at NASA. They published 2 papers in the Physics Review B recently, last year. Second, it is about one keV energy. So it's not nuclear, not cold fusion, but between. The second, we forgot to quote the experiment of Arminiuk and Kordachevsky and Kasagi about electron screening. It is published paper in Physics Review B. So some KV region. Maybe we have to look to such energy region, maybe the most proper to have some possibility to increase reproducibility. Third point, the effect is mostly surface effect. So it's the field of catalysis, as our Andean people remember us. In the field of catalysis, it's normal to have poisoning of the surface. So we have to look to such direction. Another possibility is to look a procedure to make new again damaged surface of catalysis. We think some voltage can help, but just our funny idea. So other points about just through nanomaterials like Takashi group, they have reproducibility, but the HS power was not so large, of the order of 0.2, 0.3 watt for gram. So it's good for science aspect, but not useful for the practical aspects. So the necessity to increase the efficiency of the system, but they are just through catalytic material. They show to have HS power, not expected, reproducible from one laboratory to another, but at low amounts. So we have to keep in mind all this effect and maybe find some way to collect all together, maybe catalysis at high voltage or something like that. I stop.
That's the way I try to attract students, really. I tell Rajiv, I call this field high voltage electrochemistry. Then people come and work, ready to work. If I say low energy, it's a sad thing, right? Because this whole field has so many facets. It has all possible length scales you can relate to. I mean, that makes it extremely interesting. But we have to hide and say this is so. So there's something which we have to really see how to get the next generation of students, faculty interested. I mean, we ourselves are disappointed from IIT Kanpur. We advertised it fairly extensively, but the number of people who turned up, we didn't get too many young faculty to attend this virtual conference. So there's something that I think needs to be done. I mean, I don't know, you've been thinking about all these things for a long time. So I request that some thought be put to this. And the other question, which I keep asking, I've asked almost third time. From the point of experimentalists, what is the minimal model? Is there more than one mechanism? Is there Professor Barbarian has kindly consented to come out with the proceedings for this conference. Maybe experimentalists can come together and have a manuscript on what is the minimal model for, what are the things that has to be explained. Are there some central features, which are the peripheral features, and which are the central features? If that can be, if there is a consensus there, maybe these things can be thought through. Yeah, Professor Hagelston.
I think the problem with our field from the beginning, it was described as a herd of cats, in that given the very strong animosity and antagonism for the field in general, for anybody to be in the field and to remain in the field, that they had to either be very independent or ornery or something like that. They had to be able to withstand enormous amounts of pressure. And as a result, when you have a collection of individuals that are self-selected in that way, getting them to all come together and agree on something isn't a project that's going to have a high probability of success. And then other issues, you'll find in our field reasonably general agreement that there are anomalies that are real. You'll probably find a majority of researchers to agree that the excess heat effect is real. And then if you ask any further down as to, does it require deuterium or can hydrogen work? Maybe you get a 50-50 mix. You ask, is there an experiment which is the right experiment which should be replicated, and you'll get wild disagreement. You'll get a plurality at about the 8% level or something. So your questions are reasonable questions and sensible questions, and if the effects were simpler and more straightforward, then it would have been possible to have gotten agreement over the years. But things are very multidisciplinary. They're seemingly in contradiction to well-established physical law. Mind you, that's only seeming contradictory. I don't actually believe that there's a problem with that particular issue. But as a consequence, you have experimentalists who've focused on different types of experiments looking at different effects, and certainly there is some commonality between them, but the experimentalists have in many cases moved away from models, and perhaps that's a reasonable thing, in that the theoretical questions are sufficiently tough that it's the theorists that should be putting together models that are the relevant models. The experimentalists should be putting together well-crafted experiments which clarify what it is that's going on. The most successful experimental model for my nickel is McCoubry's model, where he was able to fit excess power data, taking into account current density and loading and correction for flux.
No, what I meant was the experimentalists can have a consensus, and this is what they want the theorists to explain. If they singularly say this is a crucial experiment, this is a crucial result, others are peripheral. Anyway, I should not be talking so much.
No.
I'm not read in the literature.
Your comments are great comments, and your thoughts are good thoughts. The headache is by my list, there's on the order of 25 extremely important and probably crucial experiments that are out there. And if you talk to any individual experimentalist, if they're worth their salt, they'll explain to you that their experiment, the one that they did, is the one which is the most important in the field.
Can I jump into this discussion? I come at it from a little different perspective. For one, I'm not a professor, and so I don't have that pressure to publish. I know that it takes you can waste a lot of your time trying to convince something somebody for something that they don't want to be convinced of, and so for me, the first person I have to convince is myself, because, you know, am I wasting my time, or is this something worthwhile? Then my wife and my kids make sure that they don't think that I'm throwing away their inheritance. Um, and beyond that, we have been pretty much operating under the radar here, because, you know, we saw no reason for us to try and publish. I guess as a, you know, if you publish, it may lead to funding, but on the other hand, private companies may prefer that you not publish. So there are two sides to that equation also. Um, Ultimately, in fact, just in the last few days, Jed Rothwell has gotten pretty excited about the LEC experiments, because they seem to be pretty easy to replicate, and it's the kind of thing that you could do a lot of. There's been discussion of a lab rat that a lot of people could use, and so he's kind of pushing that. He wants us to come up with a very detailed recipe, sort of like the Galileo project that was conducted 20 years ago. Um, so, you know, maybe we're working too hard trying to get this convinced. The other thing, a couple other things, and you kind of hit on it, Peter. I am convinced if we put out a theory or model or an experiment that's bogus, the people in this community will sniff it out and be on us very quickly. You know, and I think that's good. You know, there are a lot of cats in this community, and they're all going their direction. And so if you put out something that you can't defend or that's bogus, I don't think we need to expose it to the world, or to get a reasonable evaluation of it. So, you know, the pressure to publish is one thing. What Rothwell thinks is that if we get high school students and a whole bunch of people replicating these experiments, it may lead to someone asking questions. And in fact, in the presentation that I gave, we said, you know, that low energy reactions exist, and you notice the missing word there is nuclear. They may not be. They may be a combination of a few nuclear reactions and something else that's going on. I have no idea what that is. For years, the way I defended the work that we were doing at SPAWAR, from management and people who would ask me, you know, what, this doesn't make any sense. It doesn't match theory. And I would say, well, we did the experiments and these are the results we got. We repeated the experiments and these are the results we got. We documented the experiments and we submitted them for review to a journal, and they published them. You know, we were not claiming, in most cases, we did not claim anything like excess heat. We probably didn't even mention that word. We just said, this is the experiment we did. These are the results we got. And basically that puts the pressure on them to come back and say, well, those results are wrong because our theory doesn't predict that. Well, that's fine. The experiment, or the trite description of that is theory guides, but experiment decides. Theories are prepared by humans, and whereas experimental results are controlled by God and Mother Nature. Now I ask you, who are you going to believe? And so anyhow, that's the approach that we have taken. I certainly empathize with the difficulty in getting things published. It would certainly, that if you're a university professor, this would help you get funding, because, you know, right now, for example, if you want to get funding in the global warming issue, you write a paper or proposal saying that I can show that global warming is real. If you send in a proposal saying, hey, I've got perfect evidence here and an experiment that says global warming isn't real, your chances of getting funding are less than zero. In fact, you probably get a black mark by your name for any future proposal you submit in. So anyhow, I don't have the answer. Rothwell would like to do a lot of experiments. I've talked to John Paul about, you know, we could do an experiment, publish, write a paper. He could write a paper. Andy Erickson LASL or Los Alamos National Labs could write a paper, and hopefully, people from ITTK could write a paper saying these are the experiments we did, and these are results we got, and maybe that would tip the scale. But of course, we haven't tested that model yet, but that's one approach.
Can I make a comment?
Yes, sure.
Yeah, so you see, when you say that, I mean, when somebody tells you, well, theory does not predict this. In fact, the most serious objection that we always hear is that the Coulomb barrier, that's what everybody knows about, is the Coulomb barrier. I feel that, I mean, the calculation that I presented shows that Coulomb barrier can be evaded by a modification of potential, which is on atomic scale, not nuclear scale. So that is something that, I would request the LENR community to understand. So that is actually important, because they said now they can do this calculation themselves and replicate the calculation themselves. It's a graduate textbook level calculation. Of course, it's not that easy, but I mean, still the calculation is very, very rigorous. There's no doubt. Now you do need a special wave function, but that wave function can come from, you don't need to modify the nuclear potential. You need to modify potential at the distances of a few Bohr radius. So, and that is something that people are telling me in any case. I mean, Ed Storms will tell me, that you have to have an electronic environment which is necessary in order to make this thing work. And that this is complete agreement with that. So in some sense, now that somebody tells you that this is obviously a theorem, that this cannot happen, I believe that I have broken that particular objection. I have given a very good counterexample to that objection. Thank you. That's all I want to say.
May I say a few words? I think technology will come before science. I mean, there is always a discussion, a philosophical discussion, is science before technology or technology before science? But in that very case, I think it's very clear that technology will come before. So once we have a device, that device is being sold or being ready to be sold, then theoreticians, the experiment and science will have a look at it, and then things will change. But before that, I mean, science is like a fortress, and nobody can enter there unless you have a good password. And we don't have the password because we are not in the same field. We are not making a battle in the same field. What happened recently that last year, the European Commission awarded 2 grants for 2 groups of people working on cold fusion. And that was really a big change because we were very surprised it was accepted, Actually, in the application, there was no wordings about low energy nuclear reaction or cold fusion. It was just nickel and high energy, something like that. So it was clear it was for cold fusion. And 2 groups have been accepted. One was the one I am with Francesco Celani also, and about 15 other groups. And the goal of our project is to come up with a device or close to a device after 4 years of work. The other group is more like people have never worked on cold fusion at all, and they want to do the same thing as Google did, start all over again, rediscover the wheel. So that's what they're planning to do. I don't know if they will ever succeed because you have to be really, really enthusiastic to succeed, If you don't want to succeed something, you don't succeed. To succeed is a lot of hard work, a lot of passionate people. You need passionate people to work in cold fusion, not like regular scientists who look at the clock to see if it's time to go back home or not. You have to work day and night, 24 hours a day, 7 days a week. Otherwise, you cannot do it. I mean, it's clear. I'm very lucky because my lab now is at my home, so I can work 24/7. It's great. Otherwise, there are so many experiments I cannot do because I have to be there to turn a knob. It takes me 5 seconds, but I have to go to the lab to do it. So you need passionate people to do that. And regular people who do science on a daily basis, just like make their living out of it, won't work. They will never succeed. Forget it, So I think technology will come first. Then quickly after that, the scientists have to go to after that because they have to explain what's happening. And hopefully all the people who were against cold fusion in the first days will be gone by then. They'll be all dead. Maybe we also will be dead. But the younger generation are much more open than the older generation. That's my experience. I've seen a lot of young people, you talk about that. When I was teaching, I'm retired now, but when I was teaching to my students, I was talking to them about cold fusion, and there was no problem with them. Young, they're open to everything. Now, when you have made your career about something else, and then all of a sudden, something happens. There is cold fusion. You know what? You should drop everything you are doing and should go to cold fusion. And this is very difficult because you are not a specialist in this field, and you have to start all over again. And you instead of being on top of your knowledge, you are on the bottom, and that's very hard psychologically. Change field. So they will never let us do it. Even if you publish in any peer-reviewed journals, there are tens of papers published on cold fusion in peer-reviewed journals. But when they talk about peer-reviewed journals, they talk about either physical review letters or science or nature. That's the three ones they're talking about, not the other ones. The other ones are nothing. Forget it. I mean, if you publish, there are a lot of publications in peer-reviewed journals. It doesn't make any difference at all. So that's what I want to say. Thank you.
Can I ask something?
Sure.
Okay. We got Andy Erickson at Los Alamos interested in replicating Frank Gordon and Harper Whitehouse's device, and it worked. And you replicated it, and it worked. And Andy could make this very visible, but he's not comfortable, and nor am I. We have to be sure that you can go in front of really arrogant people who know way more than us and present confidently. Okay, so Andy's criteria. This is the question because Saribin Hassan and Rout published some things. Radiation coming out. Andy said, if I can make radiation something that not just get broadband radiation, but some spectral radiation from chemical means, now I'm a little more comfortable. Okay. And so we started looking, and Andy right now is preparing the black box to look at the invisible radiation. We don't know what it is. The radiation that might come out of a working replicate of Frank and Harper's device, because Andy has them. He replicated 3 times. No, he tried 3 times and 1 failed. Okay, so he's got something to work with, and he's going to put it in a box where there's a photographic plate, the modern version, the electronic version, and he's going to look for clouding. And so Frank said, well, go look at Rout's papers. And I see Suriname Bassan a long time ago, they observed some strange, they were trying to characterize radiation that would always fog plates. And when I look at 30 years worth of data, it seems like everybody tried to fog a plate and nearly everybody succeeds. And yet, and here's where you might know more. It came up that one of the papers, the Rout paper, that had, when they put filters in front of the radiation, it didn't respond corresponding to anything familiar. And that means there's a different radiation, like the Lutz would say, strange radiation. Are we looking for something we're familiar with, or do we have to also, because we're going to, we bought the little PIN diode, Dennis Peace, who did, he looked for K alpha X-rays also. That's our direction to go look, down to see K alpha X-rays. We expect there should be. He saw none, but Saribin Hassan and Rout saw strange radiation. Tell me about what the strange part, the strange radiation that doesn't, we should be looking for that. What is it?
So
That's
I have two thoughts for you.
okay.
One is that a conjecture about that experiment, which again isn't supported by any data yet, is the possibility that you have electrons basically hopping onto molecules as the source of current in the gas. So it's a conjecture. If that's what was going on, then it wouldn't be anomalous in the sense of like Jean-Paul's experiment or excess heat experiment or tritium production or something. On the other hand, strange radiation. There was an experiment by Urtskoyev where
Yes.
sent a very large amount of current through a titanium electrode in water. And what he saw was outside of his stainless steel chamber, detectors would respond. And the response was not what you would have expected from any normal particles. So for example, you wouldn't expect charged particles to have gone through the stainless steel chamber. Neutrons in principle could go through the stainless steel chamber, but they wouldn't have interacted with the detectors the way Urtskoyev reported. My recollection is he put some mice on top of the chamber, and the mice didn't fare well. The strange radiation did them in. Again, my memory is imperfect, but anyway, there's been other folks that have reported strange radiation as well. It's conceivable that the anomalies reported by Oriani and Fisher might be considered to be strange radiation, although there's no evidence it's the same kind of thing that Urtskoyev was looking at.
So after,
Go ahead.
no, I want to say after Schrodinger's cat, we have a mice here. So, it's a very interesting experiment.
It did not affect the mice. Is that what he said? It did not.
No,
It did.
I think it did. My recollection is that it did affect the mice.
Urtskoyev's work that first caught my attention because it was strange. I think I'm thinking of the same set of experiments where he even had tracks on that were totally unfamiliar, and it went a meter through air, and then it went into if I recall, one magnetic, one non-magnetic container that he tried to detonate ammonium nitrate, and the non-magnetic reacted, the magnetic one didn't. So he was trying to differentiate. Is there a magnetic thing? Well,
can you come closer to the mic? We can't hear you. Can you come closer to the mic?
Oh, okay. Are you there? Okay. Urtskoyev had one jar that was non-magnetic, about memory says about a half a meter from the I'm going to say 5 kiloamp, 5 kilovolt into a little teeny fuse. Okay, so half a meter away, he gets a little can about that big with ammonium nitrate. In this can, it's an iron magnetic shield, and the non-magnetic one reacted, and the magnetic one didn't. And so I thought, okay, that was my first exposure. And then he showed the tracks. The tracks just didn't match anything. And then, well, a couple of days ago, because Frank Gordon said, hey, go look at the papers. I did. I went back. I had looked at them 5 years ago. I went back and looked at my notes. I missed it a little bit. They put they had put filters in front of between the photographic detector and things making energy come out, and it didn't. The particles did not get stopped when they should be stopped, or they kept going through when they shouldn't have gone through, or they stopped when they shouldn't have.
So what's needed is for somebody with some resources and some diagnostic to get a functioning version of that experiment up and start diagnosing it to death to clarify what the heck's going on.
Yes. Why has no one been able to identify? Everybody gets fogging that says there is something there that you generate with this reaction that is definitely unfamiliar. Everybody gets fogging. And yet, almost nobody can figure out what the fogging is stopped by or transmitted by. How does one?
The idea is you'd actually like to use detectors that are more specific. You like diagnostics that tell you what it is that you're looking at. Fogging a film is too non-specific.
Yes. Well, Pease, I know you might know Dennis Pease. He had published his work. Okay, he was looking for K alpha, and we thought a K alpha, yeah, we would see that. And the one that caught my attention was when Bush and Eagleton reported electrolysis, nickel, light water, with a rubidium carbonate electrolyte. He said he observed a 3.5 day half-life decay on his Geiger counter. Okay, and that caught our attention. K alpha coming out, we think, for yttrium. And he, in that experiment, this caught our attention, okay? The rubidium should have made by a reaction everybody thinks is not existent. I think it was Randall Mills.
In their experiment, they presented data showing the K alpha of palladium.
They what? They showed what?
Their data showed K alpha of palladium.
They did. Peace's experiment showed K alpha palladium. Yes.
No, but Bush and Eagleton, I at one point I did a study to try to figure out everybody who measured any characteristic X-rays or X-rays of any sort.
Yes.
And Bush and Eagleton are almost singular. They're about the only ones that ever have reported a K alpha.
Did they actually measure the K alpha from? So they got the K alpha of palladium, not silver and not cadmium, because you'd expect one of those. You expect silver K alpha also, and I didn't know they measured that.
Yeah, I do not recall other K alphas showing up in their data.
Well, it might be that the Bush and Eagleton observation is the only one ever, except it fit a particular pattern. He claimed, well, the rubidium should have taken on a proton and made strontium. So he looks for strontium and he found it.
Yeah, well,
and then
the Coulomb barrier stands in the way of protons getting close to heavy nuclei.
Well, if you conjecture, I'll conjecture that. I'll show you how. Oh, yeah, you can add a proton or add a deuteron. So then if you had strontium and you added another proton, you should get yttrium. But the yttrium should be radioactive, and it should be K alpha, okay, electron capture. And so I thought, okay, what is the half-life of that? And it's about 3.5 days. So you look at his observation, and it's clear, if you're me, okay, so I'm over here in San Diego, it's clear that 2 protons eventually ended up on top of rubidium and made something that we would say should be radioactive with about 3.5 days, and that's what they saw. So I'm looking for anything else that would do that.
If you're looking for radioactivity in these experiments, the observations that you might be interested in are 3 experiments that Kevin Wolf did that produced massive radioactive species. So Kevin Wolf measured the gammas and measured the half-lives of 3 samples that had radioactivity at the level of as I recall, many times 10 to the 15th atoms. So when the activity decayed, his neutron detector went nuts, and then the decays lasted on the order of the primary decays were on the general order of 10 days or so, and months later he was still doing measurements and checking half-lives of the decays that were slower.
What can I find this on the LENR site?
So Tom Passel published or posted some slides which gave some of the data. So Tom Passel was the program manager under which Kevin Wolf did some of his work.
What I'm looking for is something that I could go look at before tomorrow, even today. Is it anything recorded? Some conference.
Tom Passel's slides are available on the internet. They're
okay. Passel. Sure. Okay. Then what you're saying is that's the gateway to it.
Tom Passel would be the author, but the data was taken by Kevin Wolf.
Ah, okay. Good. I'll look at Passel. There's plenty of his. Thank you.
Okay, any more comments or anything like that?
May I just make small comment?
Sure.
Well, yeah, I got one more question because you guys do things. And the most important thing is the observation, okay? And one observation that will get somebody at Los Alamos and Sandia Lab, and I already probed it. One observation that you guys made repeatedly is it explodes. Will you stand by your observations that it really does explode? That there are micro explosions, macroscopic explosions, that people report the 20 micron little holes. That's it, because you want to get off this soon. But it is a serious question to us. Los Alamos will be extremely interested if you can repeatedly make it explode.
So in terms of experiments like that, there's some set of experiments reported by Didick and Wisniewski, where they came in with 25 MeV gammas on palladium deuteride and saw more massive transmutations than in any other experiment.
Did I get this right? He injected 25 MeV into the PD?
Very, very strong beam of 25 MeV gammas onto a cell that had palladium deuteride in it. Anyway, that's an important experiment. It's one which provided some motivation for the NASA experiments that were done at lower energy. So gammas coming at lower energy.
Okay. More comment from me? Okay, so for what we have seen, the cold fusion came because no equilibrium condition. So it means chaotic, but just chaotic, do almost nothing. What we need is controlled chaos. And then, so what do you want to do? Controlled chaos. Statically, nothing happened. It caused something very difficult to detect. With controlled chaos, maybe we can manage the effects. I finish.
Okay, thank you. So any other comments?
I have a question for Professor Wysotsky, if he's still around. Yeah.
Yes,
So
I am.
so there is now more than circumstantial evidence for your presence. How is it this whole LENR seen in Ukraine, Russia, and so on? Is it more prevalent? Is there some research, more networked research, funded research in ex-Russia and Soviet bloc and so on?
It is a political question. I don't know the answer. We working together with Alla Kornilova about 30 years, and we continued our investigation, joint investigation. But unfortunately, I don't visited Moscow last 6 years, but it is not a very strong influence on the result of our investigation. We're talking by Skype each week, so it is not problem for us.
Okay. Thank you.
Okay, any other comment, discussion? Or otherwise we split until tomorrow. There's another session tomorrow, same time.
Yes. Yes.
Yeah.
Okay, so bye-bye,
Yeah.
everyone. Bye-bye.
Thanks a lot for.
A good night and
Thank you.
good day, or good afternoon, whatever.
Bye. Bye.
Yes, good morning.
Okay, thank you. Bye.
Okay. Let's look at that.
So shall we end the meeting?
I think good.
Okay, bye.
Bye-bye.
Bye-bye.